The conservation of momentum. When objects interact, they do it through forces. The application of forces causes changes in their momenta. The word conservation means to keep unchanging or unaltered. This implies that if n number of objects, each of which has its own distinct momentum, were to interact, their individual momenta would change in such a way so that to ensure that the sum of their momenta before and after the interactions remained the same. Let's try to unpack that sentence. What we just stated is the principle of the conservation of momentum. To keep things simple, we shall limit our discussion to only two objects interacting. And the most readily observable interaction is collision. We see this on a daily basis. Let's say that we have two objects, one of mass m1 and velocity u1, and the other of mass m2 and velocity u2. Remember, these are the velocities of these two objects before the collision happened. The two bodies collide, and as a result of this collision, both bodies are exerting equal and opposite forces on each other in accordance with the third law. This causes a change in their momenta. We assume that the masses of the two objects remain unchanged before and after collision. So the change in their respective momenta has been caused only due to changes in their velocities. Let the new velocities after collision be v1 and v2. Mathematically, the principle of conservation of momentum states that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Or in other words, the sum of the initial momentum of the system before collision is equal to the sums of the final momenta of the system after collision. There is no change in the net or total momentum of the system. But how? How can we see that this principle is correct? We have already learned that force is the rate of change of momentum. Thus, if F is the force exerted on object 1 by object 2, then F21 can be given as m1 v1 minus u1 divided by t. Similarly, the force exerted on the second object by the first one, F12, can be given as m2 v2 minus u2 divided by t. By Newton's third law, we know that F12 is the negative of F21. These two forces are equal in magnitude but opposite in direction. If we substitute these values into this equation, at the time of collision, the t time is same for both objects, and since it is on both sides, we can remove it from this equation. Thus, we are left with a new equation, and if we arrange the terms of this equation in a different order, we get the new result m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2, which is the mathematical form of the principle of conservation of linear momentum. Let us think of a simple application of this principle. Let us say that we have an object of mass 2 kilograms which is stationary with respect to us. In other words, the momentum of this object is 0. Let us say the object suffers an internal explosion. It blows up from the inside, and as a result, the two pieces are flung in opposite directions. The question is, does the law of conservation of momentum hold in this case? If you were to actually perform this experiment in real life, you would see something interesting. If the masses of the two fragments from this explosion are identical, their velocities would be equal in magnitude and opposite in direction. So the initial momentum of the system was 0. It was stationary with respect to us. And the final momentum of the system is the sum of these individual momenta. Since the mass of the two fragments are identical and their velocities are equal in magnitude and opposite in direction, we notice that the sum of their momenta still come out to be 0, which means that the net momentum of the system has remained the same before and after the explosion.